Assalamualaikum and selamat sejahtera. We are from Group 7. Consists of 6 member. That is Elvin Lun, Aaron Marais, Jusimin, Muhammad Irsyad Ilham bin Abdullah, Amir Haikal bin Syadat, Nicholas Ken Peter, Muhammad Alif Syahmi bin Muhammad Carol, and Sheikh Adib Aiman bin Sheikh Ayub. We want to present our group project about Fourier's law of heat conductor.
Good day everyone and welcome to this Ssce 1793 special report. We break into your regular programming with a massive update from the world of engineering. A profound realization regarding the everyday impact of first order ordinary differential equations or ODEs. So before we dive into the thermal physics, let's look at the basic definitions. A differential equation is any equations containing derivatives. A first-order ODE involves only the first derivative, and it can be classified into several types depending on its mathematical structure: separable, homogeneous, exact, or linear first-order equations. But how does this relate to the heat around us? Well, we will cross over live to our colleague, Mr. Abu.
A new thermal discovery that just been found and it changed everything about heat transfer. I am here with Dr. Adam. Dr. Adam, can you explain more about what just we found today?
Okay, thank you Abu for that. So next, yes, the real world thermal management industry has been taken by storm by a legendary law governed by a first ODE, Fourier's law of heat conduction.
So the Fourier's law of heat conduction explain how does the heat move. So the energy transfer of kinetic energy between particles within a solid material without any physical movement of the matter itself is how the heat conduct. So and the direction of flow is the heat always flows naturally from a high temperature region to a low temperature region. And the founder of this by the French mathematicians and physicist Jean-Baptiste Joseph Fourier in 1822. And then let's see the factor that affecting the rate of heat flow. The first factor is the cross-sectional area. The larger the surface area, the more heat can pass through. The second factor is temperature gradient, dT over dx. A larger temperature difference between 2 points accelerate heat transfer. And the last factor is material property, that is okay. And every material has a unique ability to conduct heat.
Ouch!
What happened? What's wrong?
That handle is hot. It's almost burned my hand.
Why? My handle is just fine.
Now, let's look at how this is expressed mathematically. Fourier's law is written as dq over dt, or q equals to negative times k times a times dt over dx here, which is the rate of heat flow using what as the unit. The k here is our thermal conductivity of the material, a is the cross-sectional area, and dt over dx is the temperature gradient with respect to distance. Shall we take a look at how we can put our formula or equation into action? So, let us go down here, which I have our formula for the Fourier's law of thermal conductivity. Q equals to negative Ka times dt over dx. So we need to separate both of these. And we can do that by just put the dx to the left or with Q here. But I'm going to put a t, dt at the left side here. So we'll get negative Ka with dt equals to Q times dx. And then we'll have to integrate both sides of the equation. We'll get integration of Q dx. And then as negative Ka is a constant, it can be put outside the integration. And then the same thing for Q, we integrate dx. So we will get negative Ka with t and Q x plus c. So we have gotten to this part, we will have to find the c. And the c, it's easy. We just have to insert our initial value point or our boundary conditions here. When x equals to 0, T will be equal to T hot, the hot temperature for the hot part of the material. Initially, I say that the T will be equals to 100 degrees Celsius, but for here, I want to make an equation that we can use for different temperatures of the materials. So let us put these two conditions into our equation. Negative Ka times T hot equals to Q times 0 plus C. We'll get that C is equal to negative Ka times T hot. And we will put what we got for C back into our equation. So we'll get negative Ka T equals to Qx minus Ka times T hot. And so we just want Qx alone at either side. So Qx equals to Ka T hot minus Ka T. And you can see here that we can factorize the Ka here. So we will get Ka times T hot minus T here. And see, this is the equation after we integrate and put in our initial value points. So T is actually for the cold part of the material, and if we want just to find T, right, we will have to do this. So let us take back our equation from above. Qx Ka T hot minus T. So we'll put the Ka to the other side. It will become T hot minus T equals to Qx divided by Ka. And so it's easy. So T will be equal to T hot minus Qx over Ka. So an equation that will help us to get the temperature at any point, and this T hot here will be given by the equation itself. And that's it.
Hello. Hey guys, what happened?
You know this spoon is hot.
Yes,
Can you help?
I think you guys dilemma. Because as an engineer, we don't complain about the math, but we just find the solution.
Of course, it's hot.
So what's your solution?
Okay, wait, I found this heat insulator, which is if you take this heat insulator and you combine with this spoon, you can touch it without it burn your finger or hand. Yes, really, you can try it.
Wow,
Wow.
it really works.
Yes, it works.
Okay, now we move on to formula application, which is analysis and material comparison. In this slide, I will prove the theory using actual calculation and by comparing the two material, which is metal spoon and plastic spoon. The application of this formula, which is based on the real world. Let's take the situation of two students in the cafeteria. Both spoons have the exact same physical dimension, which is 50 cm long, and receive the same heat from the soup. The only difference is their material property, which is the K value. The metal spoon has a high K value of 16, while the plastic has a very low K value, which is only 0.2. Let's see what impact this difference in K value has on the temperature at the end of the spoon held by the student. Okay, now we move on to the impact of the difference in K value. As you can see that the K value for metal spoon is 16, while plastic spoon is 0.2. When we plug this number into the ODE equation we just solved, look at the result. For the metal spoon, the temperature at the end of the handle is still at the 78 degrees Celsius, which is very hot temperature and can cause skin burns in a matter of seconds. Conversely, for the plastic spoon, the temperature dropped drastically to 29 degrees Celsius, which is almost room temperature. This scientifically proves why plastic is much more comfortable to hold compared to metal. Okay, now we move on to the conclusion. As a conclusion to our presentation, the first order ODE is not just theory on the paper. It gives us the understanding that the material property constant, which is K, plays a critical role. Through the understanding, if we still want to use a metal spoon because it's durable, we can solve this heating issue by applying an insulating sleeve, like wood, on the handle part. This shows that mathematics is combined with engineering to solve our everyday problem in the cafeteria. That's all. Thank you from us.